Today we would like to continue with range functions in R2 and in R3, or generally in Rn. And for today we will look for range functions in R2 and R3 in infinite space. So we will look at the Laplace equation, or the Poisson equation. Laplace u is f. And then we will look for the range function that's belonging to that model. And also we will look at half spaces. And that means that, for instance, instead of an infinite dimensional space, we will look what happens if we have a half space for which, for instance, z is larger than 0, and at z is 0, we for instance, the temperature. What's the solution? Using range functions. That's our goal for today. Yeah, and also we will look at the circular domain and things like that. So we will apply it to a lot of problems. And that's the goal. And my first question is always, do you have questions about what we did yesterday? Yeah, we made a few exercises. I think most of you understood what we should do. Yeah, or could make the exercise. And then we'll continue with well, something new, and then we will continue with also some exercises. So the general problem for today will be, can we solve such a problem? In a certain domain, and let's assume that we have specified on the boundary the temperature. So the goal for today will be, can we solve such a problem? And we will look at different types of domains. Sometimes there might be not a boundary. Yeah, but the essential idea will be always, well, we have some kind of domain. We have an outward normal vector. This is the boundary. Here inside we have f, and on the boundary we specify, in this case, u is equal to gx. So if you look at this problem, then you might say we have a stationary heat problem with sources f inside. We specify the temperature on the boundary. What is the temperature inside the domain? Sometimes you might also look at the other problem, that you have a domain, similarly, but then you're looking at the outside. Laplace u is f, and u is g, x, and then the domain is outside, so then the normal vector is in this direction. Yeah? So then you look at the outside. So that's what you also can do, that you have some kind of region where you heat it up to a special temperature, and then you ask what's the temperature outside. Yeah. So that problem is also then solvable. That's a general idea. The range function for this problem has to satisfy range function has to satisfy this. The same PE, but in the right hand side, a delta function, and that function has to satisfy the same type of boundary conditions, but then homogeneous. Okay. Then we have the second identity of Green. Second identity of Green, which states that the integral over my domain D, u Laplace v minus v Laplace u, that becomes u Laplace g minus g Laplace u over my domain is equal to the integral over the boundary. Integral over the boundary of u dg dm minus g dm. Yeah, bring the second identity. And in this particular case, if you look at this problem, then you see that over here I have delta x minus x0. Laplace u is equal to f. And what do we have? G is 0 on the boundary. So over here, for this problem, G is equal to 0. And we have that U is G. And that means that we can integrate this directly because U times the delta function will give me Ux0. This integral, if I know G, I just have G times F. I can put it to the other side. Then I get the integral over my domain of G times Fx dV. And I have plus the integral of the boundary of my domain of G, small g, times dg, dn on the boundary, ds. And now it depends on what your domain is. So then you can fill in the domain and the boundary of the domain. And if you know what your Green's function is, then you have here your solution. Yeah, because your G is a function of x and x0. So once you have found your G, it's automatically you have your solution. Yeah, you don't have to do anything additional. Yeah, so solving this problem actually means that you have to solve this problem and then use Green's identity to obtain directly the solution of the problem you want to solve. Is that clear for everyone? Yeah. So it all goes all back now how to solve that problem for your Green's function here. And what I'm now going to do is I'm going to solve that problem. I'm going to solve that problem. And I start in R2 or in R3. So what do I have? Take a picture. I have somewhere my point x0. G is 0 on the boundary. Well, it's infinite space, so it's at infinity. What kind of solution do you expect? So if you look at the physics of the problem, I look at the stationary heat solution, for instance, and at the position x is x0, I have a continuous heat source that is radiating energy of content 1. What property does your solution have? If I look in different directions, so if I'm looking in different directions, for instance, is there some symmetry in your solution? Do you expect some symmetry in your solution? What do you expect? Think physics. Think in physics. If I have here a heat source, yeah? What do you expect? There is a circular symmetry or a spherical symmetry. That doesn't matter in what direction you go. So what do you expect? You expect that your solution will be only dependent on the radius and not on the angle. Yeah? So you will expect radial symmetric solutions. Okay, so that's what we're looking for. We expect radial symmetric solutions. Okay. So what I'm going to do is I'm going to consider here R2, and here I'm going to consider R3. So my Green's function in R2 will only depend on the, if I introduce for instance polar coordinates, will only depend on R. If I introduce over here spherical coordinates, rho, theta and phi, I only expect that my solution will depend on rho. Yeah? So what we're going to do here is introduce polar coordinates. And here we are going to introduce spherical coordinates. And if I do that, then my x is r cosine phi, y is r sine phi. But the most important thing is that I will have that my g is a g of only r. Yeah? And if I introduce over here, well, what is it? R cosine phi, I will take rho cosine phi sine theta, y is r sine phi sine theta, and z is equal to r cosine theta. Then I also will get that my function is only a function of rho. So what I'm going to do is I'm going to rewrite this PDE, which is in fact uxx plus uyy plus uzz if I'm working in 3 dimensions. And if it's 2-dimensional, then I don't know the derivative. Yeah. I'm going to rewrite that in polar coordinates and in spherical coordinates. Well, that's something you did, I think, many times already in your studies. I'm not going to write it down, but I'm only going to write down the PD that we then get, or actually the ODE. Yeah, I'm keeping the separation. So in polar coordinates, my differential equation becomes this. Zero if I'm not in the point r is equal to 0. And here I will get 1 over rho squared, rho squared, GER, dd rho is equal to 0. Yeah? So I assume for the moment that I'm outside the point x is x0. Yeah. Then I have these differential equations. And then I put over here 0. Yeah. Then I'm going to solve these equations. Well, what do you get? R d GdR is equal to a constant, C1. And then the next step, GdR is C1 over R, so I will get that G is C1 times the logarithm of R plus another constant C2. Yeah, and the polar coordinates, of course, are taken with respect to the point x0. Yeah, polar coordinates, spherical coordinates are taken with respect to the point x0. Yeah, to be sure, let's make a picture. If I here have my point x0, yeah, then this is the R direction and this is the phi direction. I take it with respect to that point polar. That's symmetric with respect to the point x0. Okay. The same thing I can do over here, and then it follows that rho squared dg dr is equal to a constant c3, then divide by rho squared. Yeah, I'm not in the point x is x0, so I can divide by rho, and then I will find that dg dr is equal to c3 over rho squared, and then I will find my g rho. It's early in the morning. Yeah, we have this, and my g rho is equal to minus c3 over rho plus c4. Then for both problems, in R2 and R3, the question is how can we determine the constants? And so the question now will be how to determine the constants. What property didn't I use so far? Yeah, so look at your problem. Laplace G is the delta function. What thing did I completely neglect so far? Boundary conditions. Well, at infinity there are boundary conditions, but I assume always that there is no energy at infinity, so all things are zero at infinity. Or whatever value I would like to give it over there. But if you look at your differential equation, I solved the equation here for x not equal to x0, so I put over here 0, and I neglected the delta function. And I also did not use the fact that the integral of the delta function is 1. And if you remember how we constructed for in a one-dimensional case of Green's function, I also did that. I said at a certain moment, let's consider for x smaller than x0, let's consider the problem for x larger than x0, solve the problem. And that's also what I'm now doing here. Yeah? Forget about x0, stay away from that. I can solve the differential equations. And then I had to include at a certain moment the delta function. I had two conditions. In R1, one was that g was continuous, and the other one was that I had a jump in derivatives. Well, you can now immediately see that in R2, my g is not continuous, but I have a logarithmic singularity. And in R3, I have a 1 over rho singularity. So my Green's functions have singularities. And they become more and more severe. If I go into Rn, and then it will be something with 1 over rho to the power n minus 2. Yeah? But I did not use the fact that the integral over a domain of the Laplace of g dv, that is integral over d of the delta function dv, that is equal to 1. This integral over here is of course the same as this. Yeah? The plus of g is equal to the inner product of the number operator with the gradient of g. You can work it out and you have the same. Here I can use the divergence theorem of Gauss. And that gives me the integral over the boundary of D of inner product with n ds, and that still should be 1, of course. And what I now will do is I will take a very special D. I will take a circle or a sphere, depending whether I'm in R2 or in R3. Yeah? I can always do this, because I have this differential equation, and the only thing that I'm saying now is I take the integral over a circle, both sides. That's what I'm doing. Yeah? Or I take the integral over a sphere, both sides. And both sides I put the same integral. So I'm changing nothing. What do we know if this is a circle? Or if this is a sphere? What do I know about this? The directional derivative of g in the direction n. What do I know? Well, this. Here I have my point x0. Here I have my normal vector. Yeah. What do I know about this? This is of course dg dn, the directional derivative of g in the direction n. And for the circle that's equal to, if I introduce polar coordinates, so I introduced r and I introduced phi. What is this directional derivative? It's equal to the GD Aditya? The GD, if I use polar coordinates, the GDN is equal to the GD R? Yeah, you agree? Because the GDN is the derivative of g in the direction n, and n is also in the direction of r. Yeah. You agree?
Yeah.
Okay, so in 3 dimensions, this is equal to the GD rho. Okay. So what I know is that in R2, over the circle around x is x0, my integral becomes, well, the GDR times ds. That should be 1. If I look, because this is an integral over a circle, what do I know about the GDR? Is GDR changing over that circle? No, it's constant. Yeah, because g only depends on r. So in this integral I can take out the GDR. Because it's not varying over the circle. G is a function of r, over the circle it does not change. So I can take it out. So I have the GDR. Sorry. Yeah, it should be. This, the GDR times the integral over the circle of 1 ds, and that should be equal to 1. Well, the GDR I know. Well, what is it? It's C1 over R. Yeah, I can also differentiate this C1 over R. What is the integral over the circle? 2πr. Yeah. And that should be equal to 1. Hey, R cancels. And I will find that C1 is 1 over 2 pi. That's pleasant. Yeah, I can do the same thing in R3, but now I have spherical surface. And I will have dg d rho. Yeah, dg d rho. ds, and that should be equal to 1. Over the spherical surface, dg d rho is not varying, it's constant, so I can take it out again. So I will get dg d rho times the integral over the spherical surface of 1 times ds, and that should be equal to 1. Well, what is dg d rho? dg d rho, it's still here, C3 over R squared. And then this integral, it's equal to got to write down here minus sign. It is 4 pi rho squared. Yeah. And that should be equal to 1. So that implies that my C3 is equal to minus 1 over 4 pi. So far, I found the following in R2. I found this plus, what is it, C2. And here I found G rho is equal to minus 1 over 4 pi x minus x0 plus c.
I think we don't need the minus sign on C2 because the derivative of G over rho is.
Oh, yeah. Did I do some? The G rho is this, eh? Yeah. Plus. I have here a mic, so let's see what. No. Let's see, dg d rho. Yeah, that's well. Where is the minus sign going wrong? My notes. In my notes I have somewhere a minus sign. Well, it's not important, it seems. Yeah. Well, I don't see a difference in minus sign, but perhaps my notes are wrong. Yeah? Okay. What's now the idea? Is that the next constants, C2 and C4, are they important? Are they important? What's the goal? I would like to have a Green's function. Only one. So C2 and C4 I can leave out if I wish. Yeah. I can leave out without any problem. I'm only interested in a Green's function. So here I have a Green's function in R2. Take this 0. Can be taken equal to 0, and similarly this one can be taken equal to 0. I'm only interested in one function. Yeah? Okay. Next step. Next step. What do we know?
The variable r is the distance to the origin, right?
Yeah.
And then the domain D is a circle around x0. Or?
Yeah. Where did I write it down? Here. So I take, you should see it in a different way. You find this. Yeah? I only want to determine the constants. And I have my differential equation, which is Laplace G is the delta function. Yeah? I can do with what I like with it. What I do is I put over here an integral and here an integral. And take this to be a domain D, this to be domain D. Whatever domain I choose. And now I choose here a circle or a sphere. That's what I do in this step. Yeah? I'm allowed to do that because of this. And what does it lead to? It determines my coefficients C1 and C3. Yeah?
And what's the reason that you can pull out the VGVR?
The reason is that my solution, if I compute this on the circle, then I will get this expression.
Yeah.
But G on the circle is not varying.
Which circle?
This circle. Because the domain here I have the domain, here I integrate over the boundary. I use the divergence theorem. This is a circle.
Yes.
Yeah? But G is a function of R. So on the circle G is not varying because G is a function of R. R is constant on the circle.
Yeah, but which R?
This R, the radius of this circle. Yeah, so the radius of this circle is constant. So this G is not changing. Similarly, the rho is not changing.
I thought that the R dash should be computed from the origin.
Yes, it's computed from the origin. But I take this is my domain. This is my domain. This is the boundary of my domain, the circle. But on the circle, my G is not changing. In every point it has the same value. G is a function of R. And here on the circle my R is constant, so my G is not changing. And here I integrate over the circle, so the GDR is not changing, so I can take it out. It's constant. And then I only have to compute this integral. Yeah, it's delicate, but you understand? Everyone, also the others understand? Yeah? Okay. Yeah, the minus sign should be in here, because I have minus C3.
Because we have an infinite domain.
Yes.
I think the notation of quantity of D is quite ambiguous.
No. You should see it.
Just a little zero around x0. Maybe that's what makes it fit.
Yeah, you should consider two boundaries. The boundary for the original problem is at infinity. Yeah, is at infinity. And now I only want to compute constants in this formula. This constant and this constant and this constant. Yeah. How do I do it? That's more a trick. I have this differential equation and I just integrate it. Just if I have a differential equation, let's say dy dx is fx, that is my differential equation. And if I do this, I compute the integral from 0 to 1 dy dx is the integral from 0 to 1 fx dx. Then this is always true. So what I'm doing here is I just integrate my differential equation over a given domain that I choose myself. The interval 0, 1 or the circle or the circle or the sphere. That's what I do. This is not the original boundary. Yeah? It's just, let's say, a trick to compute a constant. Yeah, is that clear for everyone? Because I take just the boundary. And here there should be a minus sign in G. Yeah, this should be a minus sign because I have here C3 1 over 4 pi and here I have minus C3. Yeah, so this should be a minus. Yeah. Okay. Is this clear for everyone?
What will you first solve the Laplace energy for the Laplace energy?
Yeah, because I don't, because of the polar coordination of the singularity at r is equal to 0. So actually I take here 0 for the simple fact that I would avoid the singularity. And where is the singularity coming back? That is over here, where I'm starting to compute the constants. Yeah, and you can also see from this formula that you have a significant, an important singularity. You cannot get rid of it. And also here you have singularity. Yeah? In the case R1, I didn't have that problem. But in R2 and R3 you get singularities due to your source. Yeah, in R2 that's a logarithmic singularity, and in R3 that's 1 over rho singularity. Yeah? But this is important. So the important thing is that you now see that in R2 my Green's function is 1 over 2 pi logarithm x minus x0, and in R3 it's minus 4 over pi x minus x0. Yeah? And that's your Green's function. Okay, let's continue. Okay, let D be a semi-infinite or finite domain. Yeah? The question is, what can we tell about our Green's function? Well, it will turn out in R2 if you're going to construct a Green's function for a semi-infinite domain or a finite domain in R2, then it always will turn out that your Green's function has the following form: a singularity, 1 over 2 pi logarithm x minus x0. The singularity that you also have in an infinite space. And your Green's function will have something additional. This function, h. And that h actually is influenced by the boundary that you're having. Yeah? And if you compute Laplace g, then you have to compute the Laplace of this expression. And the Laplace of the logarithm gives you the delta. And Laplace h, by definition, is equal to 0 in D. Yeah, so you nicely see that if you construct it in this way, then you will get Laplace g is the delta function in the domain D, where we assume that the Laplace of h is a smooth function in D, and it satisfies Laplace h is 0 in D. And that will be always the structure of your Green's function. And in R3, we have the same thing. Your g x x0 is just minus 1 over 4 pi x minus x0. You will always have that singularity in R3 in your Green's function. And it will have a smooth part plus h x x0 with Laplace h is 0 in D. And that function is a nice function, smooth function, differentiable, bounded, and satisfies Laplace h is 0 in D. And that's always the structure of your Green's functions. So in R2 this and in R3 this. So now you see how important it is that you see that in R2 the singularity is always this, and in R3 it's always this. Yeah? And then you have to figure out what your h function is depending on your boundary conditions. So I will start with an example. Let's assume that we would like to solve the problem Laplace u is f and u is g on the boundary. And in this case that means that in a two-dimensional case. Here we have y, here we have x, and we have some sources, let's say here, or you can take the source equal to 0 if you wish. Yeah, take f0, and then we give the temperature on this line. And then we wonder, what is the temperature here in every point? Can we compute it? So then first we have to compute the Green's function for this problem. So the Green's function has to satisfy Laplace g is delta and g is 0 on the boundary. So this is the problem for G. And I know that my G has the following form. G equal to 1 over 2 pi logarithm x minus x0 plus a function h which depends on x and x0. Yeah, I know that this is the structure. Well, and my domain D, of course, in this case is this. This is D, and that's the boundary of D. And if I needed, the normal vector on D is just this. Okay. G obviously satisfies the partial differential equation. If I take the Laplace of G, it will give me the delta function. Yeah? But G does not satisfy the boundary condition at y is 0. Yeah, because you have the logarithm. Yeah, actually this is, if you write it out, it's 1 over 2 pi logarithm square root of x minus x0 squared plus y minus y0 squared plus h depending on x and x0. Okay? So that's my function. I. So you can obviously see that if I'm here at this point x0, y0, and I take y equal to 0, yeah, then this expression for sure is not 0. Yeah? But I still have a choice. I have to determine h such that if I make that choice, then for y is equal to 0, this function in total becomes 0 on y is 0. Anyone an idea how to do that? And now the physics is going to help you. Now the physics is going to help you. Look at the physical problem. What does it mean? I have a stationary heat problem, and here I have a heat source in the point x is x0, which is producing heat continuously. Yeah? Or in physics, this is also called the potential equation. And this delta function describes an electron or a positron. Yeah, so I have a positive charge over here. Positive charge over here. How can I make the potential over here 0? What should I do? Think what we did also in the method of separation of variables when you had boundary conditions. If you had a Dirichlet boundary conditions and you had to extend your functions, then you got odd and even extensions, if you remember. Now you had to, in the Fourier series, using a boundary condition, you get Fourier sine series and Fourier cosine series. And if you have a Dirichlet condition, you got a Fourier sine series. And if you had a Neumann condition, you got a Fourier cosine series. So in one case you extended it even, and in the other case odd. Think about that. How should I now extend this problem? We expand the y domain, yes, with a negative source. If I do that, then what is positively coming here from this source is negatively from that other source. In total it will be 0. If I have a Dirichlet condition, in the method of separation of variables I had to extend my functions as odd plus minus. Odd again. Yeah? Simple. So my function h, what I should choose here, should be equal to 1 over 2 pi, logarithm x minus x0. Then it should have a negative sign, so I should have minus 1 over 2 pi, logarithm x minus, and that point that I now have is this point, the reflected point. Yeah? Here I have my Green's function. Is it simple? Yeah, it's very simple. Now a question. Yeah, if I take the Laplace of g, then this gives me a delta function, but also this gives me a delta function. Then I have two delta functions. Is that a problem? Is that a problem? What do you think? Is that a problem? Most likely not, else I will not tell you it. Where is the singularity due to this delta function that I get over here? It's outside my domain. Yeah? It's outside my domain E. And I should construct it, well, where did I put it? G has this form in D. And the singularity for this function is outside D. So it's a nice function in D. So there's no problem at all. Yeah, so this delta function will not be active in D, so I can leave it out. So this is my nice function, singularity, not a singularity in D. And here I have my Green's function. And now you see how easy it is, if you understand a little bit of physics, to construct very fast the Green's functions. Because now I can immediately give you the second example. So that's in between brackets, because I still have to solve the first problem. Yeah, I will do that in a moment. Yeah, so in between brackets, let now this be my D. And let's assume that I define on this boundary g is equal to 0. And here I define dg dx is equal to 0. Yeah? So in physics it means here you describe the temperature and here you describe the heat flow. So here the heat flow is 0, here the temperature is 0. And now I would like to determine Laplace g is delta x minus x0 in D, and D are those x and y in R2 for which x is positive, y is positive, and I will have g is 0 for y is 0 and x positive, and dg dx, that's also dg dn of course, is 0 for x is 0 with y positive. Yeah, that's the definition. Can you construct the Green's function very fast? Well, what do we know? My g is 1 over 2 pi in R2, logarithm x minus x0 plus that function hx0. Can you give me the formula for h? Can you construct the Green's function for this problem? Well, if I don't have this boundary, then it's that problem over there. Yeah? So to take care that g is 0 on this, I have to reflect this point here. And this is the Dirichlet condition, so it should be an odd extension. So if it's over there positive, it should be here negative. Yeah? Okay. But that's not enough, because I also have a boundary here. So I have to reflect also in this boundary. And what do I have to reflect? I have to reflect this point and this point. You agree?
Yes.
Well, this is an even extension, so positive remains positive. And this is also an even extension in this line. So this is also then negative. And now you nicely see that in this line again, positive, negative, and I satisfy all conditions. So my Green's function now consists of 3 additional terms in here. So the Green's function for this problem is 1 over 2 pi logarithm x minus x0 y0, and then minus 1 over 2 pi logarithm x minus x0 minus y0, and then take that one, plus 1 over 2 pi logarithm x minus, and then minus x0 y0, and then minus 1 over 2 pi logarithm x minus x0 minus y0. So without any hard computations, only very simple reflection principles, you can construct your Green's function. And that means that if you have a problem on this domain or on this domain, you can now write down the solution immediately. And remember that for this domain or for this domain, you cannot use the method of separation of variables. Yeah, because it's an unbounded domain. So for these unbounded domains, for the Laplace equation, we can now immediately solve the problem. Yeah? Okay. So these end brackets, and this was in between due to that. In this example, I constructed my Green's function. Now I have still to construct a solution for the original problem. So I have to use the second identity of Green. Yeah? And I would like to continue over there, so I wait until everyone has written down this. That's the most clever way, to take a picture of the blackboard. Yeah, you ready? Everyone is ready with that? Yeah? I gave my students in Delft an exam on July 2nd, and then I gave as a domain this domain. And here I specified g is 0, and on this domain dgdn is equal to 0. Yeah? That's a nice exercise also for you. So if you would like to so after the break you're going to make that exercise. Yeah? But then you should understand that the GDN, of course, is a normal vector in that direction, and the normal vector here is this. So when you're going to construct, then you have, well, you have a source somewhere over here, and then you have to reflect that point. In this line, and in this line. But then you have to do a lot of reflections. And if you do it correctly, you will have a total 7 reflection points. Yeah, so here you will have 3 initial points. But due to this, because this is 45 degrees, this is the line y is x. Oh, sorry, y is x. Yeah, then you get more reflection points. Yeah, try to figure that out. But that's something we're going to do after the break as well. Okay. I found in the example my Green's function, it's given over here. And now I have to solve this problem. How do you do that? You use the second identity of Green. Second identity of Green. The integral over my domain u Laplace g minus g Laplace u d over your domain is equal to the integral over the boundary of my domain of u the gdn minus g the udn ds. Well, in this example it's quite simple. This, in the domain D, you only have one delta function. That's in the point x minus x0. Yeah, in the domain D. Laplace u is in this example f x, and what do we have? We have one boundary, so I don't have to split it up. In this example, for instance, you have 2 boundaries, d1 and here d2. Yeah, so you have to split up the integral in 2. Okay, but in this we only have 1, and we have that u is g, and this is 0. Now you should be also careful that this integral over the boundary, in this case, you should always have your domain to the left side of your, in which you are going through it. Yeah? So if you take this domain, then you will go through it like this, and at infinity you will come back here, and then you will walk into this direction. Yeah, that's that integral. Yeah? So you should be careful in computing that integral, but here it's simple. So here you will find u x0. Take this to the other side. It's the integral over my domain D of, well, what is it? And that will be a double integral. That domain. Yeah, that's this integral, where you substitute your g. That's the g that we constructed over there. I'm too lazy to write down 4 times 1 over 2 pi logarithm, etc., etc. Yeah, you understand? Then you integrate with respect to x and y are running from these variables. And then we have here a plus the integral from minus infinity to plus infinity gx times dg dn, and dg dn, n is downward, so dg dn in this case is equal to dg dy with a minus sign. You agree? Yeah, because the normal vector is downward, and that's the negative y direction. So dg dn is equal to minus dg dy. So we will get over here with a minus sign, dg dy, and then x0, y0, dx. And here you have your answer. And if you have time, then you can compute the g dy. Here you have a y, here there is a y, there is a, yeah, everywhere you have a small y. In this case, in two places actually only, this one and this one. But if you have a more complicated domain, you have more logarithms or more 1 over r functions. But this is the answer. So if you specify f, small f and small g, then you have integrals that you can compute. And then you can compute the solution wherever you like. Is this clear for everyone? Okay. Then I think it's good to have a very small break. And then I will tell you something about how to compute the problem if you have a circular domain with Dirichlet conditions, and that's also an important example, the circular domain. Yeah, and there we will more or less repeat the same tricks. Of course you can solve the problem by means of separation of variables, but then you will have an infinite sum, and from that infinite sum you don't see so much. Moreover, the Green's function is very complicated because of that infinite sum. Okay, those of you that already followed my course earlier in Palembang, they know that I always bring something for the students. The stroopwafel. Okay. Well, I can go around, but I can also put it over there. So take one and... just one. Just one, because then more are left for here. Alright. Okay, let's have a break for about 10 minutes and then we'll continue. Okay, ladies and gentlemen, I hope that you enjoyed your stroopwafel, and it's perhaps interesting also to tell you something about the stroopwafel. It's a very old cookie out of the Netherlands, and in the Middle Ages, and in those times, it was actually a cookie for the poor people. Yeah, but nowadays not. So what they did was the bakers, when they had something left of cookies, yeah, so the crumbles, yeah, that was left over, and then they had the syrup, and what they did is they just took those crumbles, took it together, and then they pressed it, yeah, and then in between they did that syrup, and that was called the cookies for the poor people. Yeah, but nowadays it's a delicatesse, and even there are now, it's exported worldwide, And there are now, even in the United States, yeah, there are a lot of shops where they sell that even. So
Even in Starbucks.
even in Starbucks, yeah. In Starbucks they now make it as a cookie, yes. Yeah, so you see from the past something that developed in a very luxurious cookie.
And it also has a circular symmetry.
Yeah. Just in time. Okay. What I now would like to show you is how we can solve, for instance, the Laplace equation on a circle where you specify the temperature. Yeah, and you can look here inside. So you want to know what's the temperature here inside if you specify the temperature on the boundary in a stationary situation. Of course, you can apply the method of separation of variables. Then you have to introduce polar coordinates and you will find your solution in an infinite series. But from an infinite series, you know, you have to make a lot of terms to make a picture of what the temperature really is. So a lot of it converges very slowly. Yeah. What we will show you is that you can write down using the second identity of Green. When you constructed your Green's function, you can write it down in a very compact form. Moreover, this is now the domain. You can also say, I'm not interested in the inside, but I'm interested in the outside. So if I specify the temperature on the boundary, what is the temperature outside? You can also do that. And if we know how to solve this problem, together with the problem with the half spaces like this, then we can also look, if we know how to solve this, we can also look at domains that look like this. So if I take part out of a circle, yeah, you can also solve that problem. Also, if you understand how we do this, you are able to solve problems like this, if your domain is, for instance, this. Or part out of this. So only this. So if you know how to solve those problems, it's easy to construct Green's functions. Yeah? Whereas it becomes rather difficult if you use separation of variables. Yeah? Moreover, yeah, it's a very efficient way to do it. But okay, we have to understand what's going on. So for the Green's function, we have to look at this. Laplace G is delta x minus x0, and G is 0 on the boundary. And that's the general problem that we always have to solve. And in this case, we have to solve, that's a sphere. This problem, G is equal to 0. And here we have somewhere our point x0. Yeah, that's where we have our source. And now the interesting thing, of course, in 3 dimensions, your G is of the form minus 1 over 4 pi x minus x0 plus a function h which depends on x and x0. Yeah, that's the structure of your Green's function in R3. Yeah, we are working in R3. So we know already the structure. We only have to construct h such that the function is 0 on the boundary. Well, and now the interesting thing. We have, of course, here now a minus sign, so let's assume that we have here a minus charge. And what Green did was the following. He did the following experiment in thought. He said, well, I know how to do it for problems like this. So if I have a Dirichlet condition, I have to find its reflection point. So what he said, well, was let's assume that somewhere, I don't know where, I put a charge. I don't know where, so I call that position x0 star. And I also don't know what the charge should be. Let it be Q. And that was the experiment, or what Green actually tried to do. And that's typically what you do in research. You try something. In 99% of the cases it does not work, but in 1% it works, and then you have a nice result. Yeah, and this is what he did. He said, well, let's place somewhere another loading, another charged particle, for instance. I don't know the position, let it be x0 star. And then he said, actually, my g is so then equal to this, minus 1 over 4 pi, x minus x0, and then plus q, and then 1 over 4 pi, x minus x0 star. And the condition that he required was, of course, that if x is on the boundary of my domain, this function needs to be 0. Yeah, that's the only condition. And let's try if we can do that. Can we find a q? Can we find a point x0 star? That's all. Okay, let's work it out. So we get minus 1 over 4 pi x minus x0 plus q 1 over 4 pi x minus x0 star. That should be equal to 0 for x squared plus y squared plus z squared is 0. Work it out. Take this to the other side. Yeah, no. What?
A.
What?
X squared plus y squared is A.
Sorry, x squared. Sorry. Yeah, thank you. Yeah, so on the circle, on the sphere, we should have this condition. Okay, so let's put this to the other side and then work out with your denominators, and then you will find that q times x minus x0 should be equal to
X minus x0 star.
let's see, take the other side, x minus x0, yeah, x minus x0 star. Yeah? Then we square this expression because this is the square root of something, so we square. So we get q squared times
X minus x0.
Yeah, that's what you get. And then we work this out. So that's a little bit of work. Yeah, so we will get q squared, x squared plus y squared plus z squared plus x0 squared plus y0 squared plus z0 squared, and then minus 2
Minus x. X0 plus y0.
Yeah, that's what we get. Is equal, other side exactly the same thing. X squared plus y squared plus z squared. So this is still nasty work. What do we know? X squared plus y squared plus z squared is a squared. And also here I have a squared. This is the length of the vector x0. Now, so this is x0 squared. Similarly, this is the length x0 star squared. If I look carefully what I have over here, then I have over here the inner product of the vector x with x0. Yeah, so here I have x inner product with the vector x0. And similarly, here I have inner product of the vector x with the vector x0 star. Yeah, this has nothing to do with partial differential equations, this is just doing some nested computations. Okay. Now I'm going to rewrite it. What I will do is I will put this and this on one side of my equation. And what is depending on x, a point on the circle, I will put to the other side. Yeah? And x, the x vector is an arbitrary point on the surface of my sphere. Yeah? So the x is a, then I put it in one side. So what do I get? I will get q squared times a squared plus x naught squared, that's this term. Then I take this to the other side, so I get minus a squared minus x0 star squared. And on the other side I will have my x dependent, so if I take that to the other side I will get 2 times x inner product with...
There's a q squared also.
Yeah, you're right, the q squared is coming here. And then I have the other one minus
X naught.
yeah, then I get this expression. Okay. And I wait until everyone is so far written this out. Okay. First of all, we observe that x is an arbitrary point on the surface of the sphere. So that point can vary. Now we look at the other points. Q assumed to be a fixed value, yeah, of the charge. A squared is the radius of the sphere, fixed constant. I would like to know the solution in the point that I determined. That's a fixed point, that's not varying. That's not varying, and where I put the charge is also not varying.
Yeah.
So the only thing that is varying is that point here. Okay, now the following reason. So this is constant. This side is constant. Here I can vary. So I can change the right hand side to whatever value I like, and that's impossible. Unless this is equal to 0. Yeah, you agree? That's the reasoning. Yeah, so this is constant, this is varying, this is constant. If I change this, then this value can change. That's impossible because it should be constant, so it's only possible if I change this, that this has to be 0. Okay, so this has to be 0. So it follows that x0 star should be equal to q squared x0. That's nice. So now I know that the position of the charge will be what is called collinear with the point x0. That will be on the line from the origin and the point x0, and then somewhere it will be on that line. Yeah, collinear with x0. Okay, but if this is 0, then of course this also should be 0. So q squared, a squared plus x0 squared minus a squared minus q squared x0 squared should be 0. Okay, that's equivalent follows that q squared a squared plus x0 squared minus a squared minus q to the power 4 times x0 squared is equal to 0. What's the only unknown in this equation? A is known. The point where I would like to know the solution is known. So the only unknown in this equation is q. Can I solve this equation for q? Yes, because it's a quadratic equation in q squared. Okay, so I can solve this equation for q. Then it follows that q squared is equal to, well, minus a squared plus x0 squared plus or minus the square root of
a squared minus 4 times a squared.
Yeah? Yeah, correct, yeah? And then divided by minus 2 yeah? Okay, I can rewrite it a little bit. Minus signs changing. So I get a squared plus 0 squared minus plus divided by 2 x0 squared. And here you see that you subtract, if I compute this, I get 2 times a squared x0 squared minus 4. So I will get over here a squared minus x0 squared. x0 is within the circle, so that's not a problem. Yeah. So I will get over here plus a squared minus x0 squared. Yeah, you agree? Okay, then I make the 2 choices is equal to, then I will follow the minus sign and the plus sign. If I follow the minus sign, then I will get minus a squared that cancels, minus plus it becomes 2x0 squared divided by 2x0 squared, that will give me 1. Yeah? And if I take the plus sign, I will get a squared over x0 squared. Yeah, you agree? Okay. So take the picture again. x0, x0 star. What does it mean if q squared is equal to 1? Then x0 star is x0. So what you do is, if you have a negative charge over here, you put a positive charge on that point. That's mathematically correct. Yeah? So you get rid of your source again. Yeah, so mathematically that's the correct answer. But we would like to have the image point, the reflecting point, outside my domain. Yeah, so this gives me a point inside the domain. I'm not interested in that. That's inside domain. Yeah, so cancel. Then look at this point. This point is really outside the domain because a squared divided by x0 squared. x0 squared is within the sphere. This is the radius of the sphere, so that's really outside. So what I find is that I should take q squared equal to a squared over x0 squared, and then I find also my point, x0 star is equal to q squared x0. So then I constructed my Green's function. And here I have my Green's function for the circle. How nice it is, how simple it is. Compare that with the Green's function. If you apply separation of variables, then the Green's function will be an infinite sum. Beauty of mathematics, I would like to say. Such a nice, simple expression. And now still we have to solve the problem. Laplace u is 0 and u is equal to f. Yeah? And then you just apply the second identity of Green. Can we do that? Yeah, that can be done very fast. Second identity. Second identity. Integral over d. U Laplace g minus g Laplace u dv is equal to the integral over the boundary of u dg dn minus g du dn. And then you have to compute these integrals. Well, in this case, this is the delta function. In this example, Laplace u is 0, so that means that this is 0. We have on the boundary that u is f and g is 0. So we find as a solution for this particular problem that the solution in the point x0 is equal to the integral over the boundary, which is the circle. And that's an integral from 0 to 2 pi. Yeah, if you go over the circle, sorry, it's not a circle in this case. Yeah, you should have a sphere, a spherical surface. This integral, yeah, and then you should compute dg dn, which is equal to dg dr, and you will get over here your f times dg dr, and then you will have to compute this. Is this correct or not? This is a surface integral, huh? And of course, on the surface, I have the coordinates t by v. It's dx dy and dx dy. What I'm missing? Jacobian. Yeah, so I should have here also the Jacobian. Don't forget it. Yeah? Okay, but then here you have your answer. And you have a nice representation for a circle. One of the exercises that you can make, well, I write down a few, and I will write down an extremely difficult one. Oh.
I want to ask, but can I draw something?
Yes?
It's not quite physically, I imagine this is from the negative source.
Yeah.
So I think,
Well, this is negative charge.
I think this
This
is
positive.
So I think it will be neutralized.
Yeah.
Everything here. So it will be 0 here. But how about the other side?
The same thing. Because that's the interesting thing. I did not show you that, but if you use Maple Mathematica, whatever, you can draw the lines around this point. Yeah, and then at a certain moment you get the circles that, yeah, and then it's due to this point, it cancels. Yeah? So there are circles around from this point. You should take a circle that's going here, this point, and then it's cancelled. And that's the interesting thing. It's so beautiful because it's doing this actually. It cancels all the points. Yeah? And it's hard to understand that it's doing it. But you can see from the formulas, I started with g is 0, minus 1 over 4 pi x minus x0 plus q divided by the same expression more or less, is 0. I solved that. So I know that for each point on the boundary it's 0. So indeed those circles, this point and this point, is cancelled by the circle, that larger circle from that. Interesting, eh? Yeah. Mathematically we know it's true. Yeah. But you can also make a plot, try to make it in Maple Mathematica, and then you can see that those circles indeed, and then use the values, because the charges are different. Yeah, and then you nicely see that it gives you 0. It should be 0 because that's also how we computed it. Yeah? Okay, good question. Exercise. The first exercise is a problem that you have this infinite domain. On this boundary you will have u specified, and on this boundary the udn is 0. Yeah, you can also take the udn as g, then I make the exercise a little bit more difficult. Yeah, so if you do this, it becomes a little bit more difficult. Okay, so this is the first exercise that you can make. The other exercise is out of the book. And that is exercise, so this is the first exercise. The second exercise is out of the book. Make exercise 9.5.19. And there you have a domain which is half a circle. Yeah, with on the boundary, if I remember well, g is 0 on the boundary, and then you have to determine a solution for this domain. Yeah? And then you have to do the reflections with respect to this line and what Green found. Yeah, so one over there, yeah, reflection on the other side. Think about that. That's the other exercise, and then the difficult exercise. Then the difficult exercise at number 3. Okay, ladies and gentlemen, let's look at the exercises. The first exercise, the difficulty is first that you have to find the reflections. Yeah, but I told you already something about it. Yeah, you should find 7 reflection points. Yeah? Then the difficulty is in determining u, that you correctly compute the integral expressed in integrals over f and g, small f and g. That's another difficulty. Yeah, so be aware that if you integrate this, then you do it in the correct direction. 9590 out of the book is combining the reflections for half spaces and spheres or circles. Yeah? And I think this is a circle. There is an additional complication, but I will tell you that later. For this problem, the first exercise, the one part you can do. I'm also interested in those students that are able to find a solution for this one. So this is the most difficult one. Yeah, so that's for a Robin condition. Yeah, so the first part is not for a Robin condition, but the second one is for a Robin condition. And that's an extremely difficult one. Yeah, and I can make the exercise a little bit more difficult by looking not at the half plane, but the quarter plane, and then define normal conditions on that. Yeah, so that can be made more difficult as well. Then a final remark, if you're working in R2 and you would like to have the Green's function, then that Green's function, you should remember that on the circle, you still would like to have that minus 1 over that minus 1 over 4 pi x minus x0 plus q is 4 pi x minus x0 star, that quantity still needs to be 0, whether you work in R2 or in R3. Yeah, this has to be 0 on the circle. Yeah? But what do you have as as a Green's function in R2? That's a logarithm. So what you should do is you should take actually both to the same side and multiply, and you get q times x minus x0 is equal to, what is it? X minus x0 star. Yeah? And now you should take the logarithm, both sides, and divide by 2 pi, and then you construct automatically your Green's function. Yeah, so if you now take the logarithm, both sides, but then you get the logarithm q in your Green's function. Yeah, so if you want to compute it in R2, use R3 and then take the logarithm of this, and then you have also the Green's function for that. Simple, huh? Take the logarithm, so you get the logarithm x minus x0 plus logarithm q is equal to logarithm x minus x0 star. Take that logarithm to the other side, divide by 2 pi, and you have your equation that satisfies the boundary condition automatically. Yeah, so you don't have to do much calculations. Yeah, but then you have a logarithm q additionally in your equation. That's the only complication that you have here. Okay, you can take a small break and then make exercises. And this one is extremely difficult. Yeah? Okay. Line tells you that you have a reflection point over here and a reflection point onto that, and then you get a reflection point over there. And then you can check that all the conditions are satisfied. If I give you a quarter circle, yeah, make it more difficult, take a quarter circle. For instance, this quarter circle, then here you have a point. Due to the circle, you will have this point. Due to this line, you will get this point reflected and this point reflected. Because of you have this line, this point needs to be reflected, this point needs to be reflected, this point needs to be reflected, and this point needs to be reflected. And then you check again, and then you see that you have all the reflection points. Yeah? This is not, has nothing to do with partial differential equations, but this is just mathematics. Yeah, pure mathematics. Yeah, but this is the way how you construct easily your Green's functions. Okay, then the exercise. So then you found over here all your Green's functions, and I found that a lot of people wrote it out, so you get a lot of logarithms. Yeah, but just call it G to avoid writing down all your logarithms. And then you have to use the second identity of Green. And then it depends what I do, if I define on y is x the UDN, or if I define on y is 0 the UDN. Yeah, what the difficulties might be. But in this problem you should be aware that the normal vectors, the outward normal vectors, are this vector. That is the vector 0, minus 1. And on this, your normal vector is equal to 1 over the square root of 2 minus 1, 1. Yeah? And that's the one that you use. And if you look at the integral on the boundary, so in the second identity of Green, you get that integral over the boundary. It now consists of actually 3 parts. This part, the part at infinity, and this part. And you walk through it in this direction. Yeah? And if you compute on this line, for instance, the GDN, if it's necessary to compute that, then the GDN on this is equal to the gradient of G inner product with N, and that will be the GDX, the GDY, with your normal vector, and in this case it's 1 over the square root of 2 and 1 over this. Take the inner product, and then you get something with the GDX and the GDY in your expressions. Yeah, and so you can solve it. Yeah, use the second identity of Green, and then you're ready. And the same thing in this exercise. And here, this part you can make immediately because then you get an even extension. Yeah, so, but then the difficult one is over here. And then you have to think how to do it. Yeah? I can even make this exercise more difficult if you want to do that. Yeah, and I can also do it for a circle. Yeah, but the problem is in the fact that you have over here a Robin condition. And physically those conditions are relevant because a Robin condition means that the heat flow through the boundary is proportional to the temperature. And if you have a problem for U with a non-homogeneous term in it, then you actually say that, for instance, the heat flow through this wall to the outside is determined by the temperature here and the temperature outside. And here in Indonesia, you usually have that the heat flow is coming from outside to inside. And in our country, usually the heat is going from inside to outside. Not at the moment, because now the temperatures in the Netherlands are higher than here. For a few days, but from Saturday on it will be 22 degrees again. Yeah, but now it's 38, so my wife is complaining. Actually, she's complaining about the fact that we do not have an air conditioner. So I made a picture in my room of an air conditioner and a picture of another room of an air conditioner, telling her that I have an air conditioner.
It's so cold here.